One common use of transistors is as amplifiers. Current amplifiers, signal amplifiers, however you want to look at it. Now, transistors as amplifiers and amplifier circuits could be a 10 to 15 video series leading all the way up to the op-amp. We'll get there eventually. Right now, let's start small. I'm not trying to create a specialized series on audio and other signal amplification. I'm trying to cover a broad range of topics because this is more about exploration and discovery of what electronics can do, or what you can do with electronics, rather than having one specific purpose in mind. There are plenty of channels specialized in certain things, like the Technology Connections channel, which is pretty good if you're looking for anything to do with either streetlights or television signals. So as I mentioned in my Basics About Transistors video, transistors, BJTs, the regular ones, not MOSFETs. Regular transistors are current controlled. You forward bias their junctions to set their operating mode, and then you turn up and down the current on the base to turn up and down the current that goes through it. And the real trick is that these are two different currents. So let's use our good old standby, the NPN transistor. You'll be using this for most things you do. PNPs are important, and in some situations they're equally important. But NPNs are just a whole lot easier to work with for various reasons, especially with microcontrollers. The current goes through the base and the emitter, and it's completely disconnected from the collector to emitter current and the collector voltage. So you can have a completely separate voltage connected up here and use it as a switch, an amplifier, whatever. Whereas with the PNP, you have to do some trickery to make sure it works right. So the NPN is easier. So let's say you have a load, and you have your power, which goes to the negative end. Very simple circuit. This could be a switch or an amplifier. But this on its own, if we forget this is just your load circuit, right? Your load already has resistance, whatever's going on in it. But then you have your microcontroller. Your microcontroller has its own connection to the power, and then you connect an output pin through a nice resistor into here. This is actually versatile enough to act in all three capacities of a transistor. This can be an amplifier, a digital logic element, or a digital switch. In this case, we're going to use it as an amplifier. So your transistor, assuming you're forward biasing this junction, the base to emitter junction, let's say it takes 0.7 volts. So if you want the transistor off, you put 0 here, and of course relative to ground, and your transistor's off and the load is doing nothing. If you turn the voltage up to about 0.7 or so, the transistor will turn on, and then you'll have pretty much the minimum going on. Let's say you have 1 volt. Let's say you set this at 1 volt. So you'll have 0.7 going through the base to emitter junction. Remember, it's a forward voltage drop just like a diode has. So it takes its 0.7, and then it's running, but then you've got 0.3 left over. So this resistor is taking the 0.3. This ohmic device is taking all the rest of the voltage available after the non-ohmic devices take theirs. So you've got 0.3 volts, and then you've got whatever resistance, and that determines how many amps are going through the whole circuit. Because the transistor essentially reads the current. It is controlled by the current. It does not specify the current. It has a voltage drop, and then the current is set by the resistor. So the current will be whatever, and then there is a formula. IC equals beta times IB. C is the collector. In the NPN, that's essentially the input of the main part over here. The base is the control knob, and the emitter is where they go. There's another formula. You'll see this. You'll see these two together wherever you see transistors. IE equals IB plus IC. In other words, everything's going out the emitter, according to conventional current. The base current through the emitter, collector current through the emitter. It's just saying that the current coming in here and the current coming in here equals going out there. First of all, that's obvious. Second of all, that's Kirchhoff's current law. So, yeah, I should hope you would remember that one. This is the important one. What is beta? Beta is something that's in your spec sheet. Beta is a factor. It's a proportion. The base current is set by your resistor. And so is the maximum current here, this resistance in this load. All right, so let's say there's 0.2 volts dropped by the collector to emitter pass-through. So if this was 5 volts, you would have about 4.8 volts left. And then just like over here, you've got whatever voltage and then whatever resistance, which gives you your current. That gives you your maximum current. The transistor, if it's in active mode, right, you're forward biasing the base to emitter junction, but not the base to collector junction. This is the full voltage and this is lower, right? This is not forward biased through here. That's how the amplifier works. So this current is IB, the current through the base to the emitter. Beta is in your spec sheet. It's just based on the construction of the transistor. Multiply the two together and you get the collector current, the current going through this part. It's that simple. It's literally that simple. That's why it acts like a control valve or a throttle or whatever you want. Now, if you don't have a spec sheet or you don't feel like looking at it, you can just plug some resistors into your circuit to control the current and figure out beta from there. Because remember, we've got 1 volt here. This is taking 0.7, base to emitter is taking 0.7, so this is taking 0.3. If we increase or decrease this resistor, it's still taking 0.3. The current is changing. The voltage is staying the same. The resistance is changing, which means the current is changing. So you can make this a 1000 ohm, 150 mega ohm, whatever you want, to change the current. That's one easy way to test. You can use a potentiometer to do that. And the other way to do it is to change the voltage. Now, a lot of microcontrollers don't have regular voltage output modification. They use PWM, which is just turning it on or off, which gives the same effect, but it's not this amplification. You're getting a certain current through, just like you're turning on and off an LED, but it has nothing to do with the amplification by the transistor. It's just you're turning it on and off, so however long it's on versus how long it's off is the proportion. Whereas if you have a microcontroller or a voltage divider or whatever that can actually change the voltage, or you have a knob using a potentiometer that's acting as a voltage divider, for example, then you can change the voltage while keeping the resistance the same, and that also changes the current. It's just Ohm's law. It's just our good old standby. Now, the other mode is saturation. This is where we've got it on, so base to emitter is forward biased, but base to collector is also forward biased. So this voltage is however much higher than this voltage. That would be saturation mode, where this acts like an open wire, and it doesn't matter what the base current is, it's just going to let it through. If this voltage here is higher than this voltage by whatever number it has to be for that transistor according to the spec sheet, then it's just going to let it through and the current does not matter. But here's the thing, you don't have to enter saturation mode usually to be saturated, because again, there is resistance here to this load. Whatever's going on is not a short circuit, literally. There's some limit. You know, it may be an LED with a resistor, so you have a certain maximum current through the LED. Or it might be an inductive load with a motor or whatever. There is some limitation here. So what happens is, beta can be big. Beta can be 50 to 100 to greater than that. So 1 milliamp can become 100 milliamps, or even more. So what happens is, let's say this can only run 30 milliamps through it. You know, if you took this away, if you took away the transistor and just ran the thing, it would run at 30 milliamps. So if your beta is 10, which it won't be, it'll be higher, but let's just say 10. So you've got a maximum of 30 milliamps here. If you have 3 milliamps going through here, you've already reached the maximum. So you're going to reach saturation, usually, well before you're actually having to apply a voltage to get there. Remember, voltage and current are two different things here. They're intimately connected in Ohm's law, but this is a non-ohmic device. In order to enter saturation mode, you only have to forward bias this junction. And then whatever the current, however small, it will be forward biased. Now, how you get that voltage will also determine how you get that current, because somewhere you're going to have resistors. But it's important to divorce that in your mind. Saturation, because this has already reached its current limit and it's not going to generate any more anyway, is different than actually saturating the transistor, because having this thing in true saturation mode affects the turn-off time and other things. Whereas if you just turn the current up high enough, then it's just in active mode and you're already done. Now, one thing you can do, if you find that you're reaching that, let's say your microcontroller only puts out 5 volts to 0. So you can figure out what your maximum current is, and then you can set your resistor as high as you can to get that current. So, because a higher resistor is going to dissipate less power. Because the voltage is staying the same, if you increase this resistor, it dissipates less power, because power is voltage times current. And if you increase the resistance, you decrease the current while you keep the voltage the same. V equals I R, P equals VI. So P equals V times V over R equals V squared over R. If you keep the voltage the same and you increase the resistance, you decrease the power consumption. We're keeping the voltage the same because we have a voltage this is putting out, this is taking a voltage when it's forward biased, all the rest is here, and that's not going to change. So you can figure out what is the maximum current you need here to let all of the current through here, pick a resistor, to make that happen. And then you can use PWM to turn it on and off. So when it's on, it's letting through the maximum with the minimum current here, maximum here, minimum there. And when it's off, it's not forward biased and there's nothing there anyway. And that's how PWM works with any sort of load that supports being switched on and off rapidly. And for the record, this is called a low side switch because it's on the low side of the load, the low voltage. We'll go into switches in another video. This one's about amplification. This is about the active mode of the transistor. But just to emphasize that this will usually reach saturation when it's not in saturation mode, just because this is not putting through a horrendous amount of current and transistors amplify a lot. So this is why in digital logic you'll see that this is 5 volts and this is 5 volts, which is not forward biased, which is not saturation mode, but it's considered fully on. That's why. If you're applying the same voltage here and here, if this is 5 volts, if this is 5 volts, you're going to be saturated, unless you've got the most ridiculous load here. So the circuit I'm going to show you is simple. The base connection is going to be just a simple connection through a resistor of changing value. I'm going to use different values to set the current to turn the transistor on and off. And then your load is just a resistor and diode, fairly standard. Now what we're going to do is change this resistor value in order to change the current going through, because the voltage will be the same here, voltage will be the same here, so this will take the rest, and changing the resistor changes the current, to show you the amplification effect on an LED. When the power is connected to high, when this is connected to high, it will be on. The transistor will turn on. When I connect it to low, it will turn off. PNP is backwards. So if we have a PNP transistor here, we've got the same thing. We've got the transistor, and then we've got the load. I'll explain in a future video why I flipped it, but it's the same thing. It's just going through this way. But here, you'll notice plus and plus. Remember, it's forward biased in the opposite direction. The emitter to base junction in this is not forward biased. It's at the same voltage. Without current flow, there is no resistance, so the resistor is not dropping any voltage right now. You've got the same voltage. So it's not forward biased, it's not conducting. If I connect it to negative, now it will conduct, because PNP is backwards. Forward bias, the base to emitter junction, which lets that through, and I'll show you. So I have here an NPN transistor and a PNP transistor. Now these come in those little half circle when viewed at the top packages, and I just used the little diagram to see how it works. So basically, on these, pin 1 is always the emitter, pin 2 is always the base, and pin 3 is always the collector. So if I take the flat side of the NPN and put it that way, and I take the flat side of the PNP and put it that way, then it matches the circuit diagram, where the current is always going down this way, just for my mental ease. And also it makes it clear which one these are when I'm going to put them away, because it's just tiny little black packages with a little bit of stamping on them and it's hard to see. So I will turn on my power, which is set to 5 volts, currently no amps, and I have a set of resistors. These are 1,000 ohms, this is 10,000, this is 150,000, and this is 1 million, 1 mega ohm. I also have a blue LED. And so what I will do first is use the NPN transistor. I'm going to take positive of the power through a 1K resistor. Out of that resistor, into the LED, back out of the LED, the negative end, into the input of the transistor. I will say input and output just to make life easier. I'll say input, output, and base. For a PNP transistor, the input is the emitter, the output is the collector. For an NPN transistor, the input is the collector, the output is the emitter. If I just say input and output, it's a lot easier. So into the input of the transistor. The output will be connected over to negative power. And I will turn on my current to 10 milliamps. It immediately goes up to 5 volts, and the actual output is 0. This is not conducting. The LED is not on. There is no base connection. This is why an open switch works fine. So I will connect from positive power through another 1K resistor, and from that resistor to the base. And the LED is on. The whole thing is drawing about 6 milliamps. If I switch the input over to the negative, unsurprisingly, it does not come on. Now let's see what's actually going on here. So I'm going to replace a wire with my multimeter. I'm going to set this multimeter into current mode, measuring 20 milliamps or less. The positive probe will replace the wire connecting positive power, and the negative will replace going into the resistor. This is the collector to emitter. This is the input to output current. So this is going to show us that current. Then this one, also 20 milliamps. And this one I will replace this wire, the wire that is taking the current from power through a resistor into the base. And I'm sorry, this one is not backlit. So this meter is showing the current going through the load, the LED. This meter is showing the current going through the base. So I'll now turn it back on, and we will see. Going through the load is 2.23-ish milliamps. Going through the base is 4.15 or so milliamps. That's greater. I thought this was an amplifier. It is. Remember how I said it's saturated? I've got the same resistor here, but this resistor with the LED is dropping less voltage, right? Because your LED is taking up however many volts, so the resistor is dropping fewer volts. If you keep the resistor the same, drop the voltage, you drop the amperage. So the maximum current is much lower than the base, which has just got the 0.7 or whatever for the transistor base to emitter junction, and then the resistor is taking all the rest. So what if I change the resistor? Instead of a 1000 ohm, I do a 10,000 ohm resistor for the base connection without changing the connection to the LED. All of a sudden, you'll see this is the same. This is still 2 point some. We'll do it again. The original resistor, the load is doing about 2.23. That's the 1K. Switch to a 10K. It's doing about the same. But now we're down to 0.42 milliamps, less than 1 milliamp, and it's still putting that much current through. Not interesting yet, you say. Let's move to the 150,000 ohm resistor for the base to emitter junction. Now, this is down to 0.02 milliamps. Let's increase the sensitivity to microamps. This is getting 28.3 microamps. That's it. This is what would be coming out of your microcontroller, because this is connected to 5-volt power right there. And see, the overall draw has dropped, but this has barely changed. It's still at 2.16. It was at 2.23. So we've finally gotten down into the region where we are below effective saturation. We were never in saturation because the base to collector junction would have had to have been forward biased with a higher voltage on the base than on the collector by whatever amount to put it actually in saturation mode, which would let this act as a switch, and this would be at its max. 28.3 microamps is enough to get 2.16 milliamps through this LED. This is not the combined, right? That's the combined. Now, why is this reading 2 milliamps and change, and this is reading less than 1, and that says 5? Because it's a cheap Chinese power supply. It's doing its best, but it's basically close enough. The more power you have going through it, the more accurate it is. It has trouble with small numbers. And there's also some dissipation, of course. The transistor is dissipating some power. There's resistance all over. This is only measuring before it gets to the transistor. So there's some waste going on that is going to increase the number a little bit, but mostly it's just a little inaccuracy. These are giving better numbers. And let's go ahead and write this number down. We have 2.16 milliamps from 28.3 microamps, right? We're pretending that spec sheets don't exist. I'm going to now switch to the 1 mega ohm, 1 million ohm resistor. Mega ohm is still pretty bright. Blue LEDs are generally bright, but now we're down to 1.33 milliamps over here and only 4.2 microamps over here. So let's write that down. 1.33 milliamps, 4.2 microamps. This is the amplification. I have less current going through here, which means less current going through here until I reach the maximum of just letting it through as a wire. So you can have a big resistor here. Now, the higher your resistance, the lower your response time. Resistance has many effects. Everything in electronics has many effects. But one of them is the more resistance you have, the longer it takes the circuit to respond to a change in voltage. So if you're using PWM on your microcontroller to affect this, it's not going to work as well. I think it probably would still. We're just talking about an LED here. But if you had a smaller resistor and then you just turned it off more often, you would get the same effect with a better response time. That's the thing to keep in mind. If all you want is an on and off switch, then pick your biggest resistor you can that'll still turn this thing on to the level you want. So I would probably do something like a 300k ohm, maybe 500k ohm. It's plenty bright already. But then again, I don't like my LEDs very bright. And you can see 4.2 microamps, even at this level, I consider this bright enough for indicating something. So I could even just go with the mega ohm, and you're only losing 4.2 microamps through this resistor, plus a little dissipation by the transistor, and that's only when it's on. So that's why this works so well. So let's do a calculation. Remember our beta IC equals beta times IB. So let's do the first one we had. 2.16 milliamps divided by 1,000 is amps. So that's 0.00216 amps. Divide by 28.3 microamps divided by 1,000 gets us to milliamps, divided by 1,000 gets us to amps. Our beta is 76.325. Let's write that down. 76.325. So that means the output current is just over 76 times higher than the input current. What about the other one? 1.33 milliamps divided by 1,000, and then divide that by 4.2 microamps divided by 1,000, divided by 1,000, and we're getting 316, because our current there only dropped by about half. 2.1 some to 1.3 some. This one dropped by an order of magnitude, 28 to 4. So again, you have to account for things like this, especially the lower numbers you have. Beta, like everything else, is going to be approximate. If you need exact values, set up the circuit, put it exactly how you want, and then measure it. And then realize every single device you make is going to be slightly different. So the only device that will ever work the same way as you measured is the one you measured, and only for a while until some small quantum mechanical effect wiggles it, and then beta becomes 76.1 instead of 76.2. So in this case, I would expect beta to be maybe 100, 120 some, and that's a good enough approximation to get the current through. These are not $1,000,000 transistors. If you need more precision, you get better quality transistors. This will work perfectly fine for making your robot. They're not going to work for Intel, but they'll work for you and me. But that's how beta works. The base current times beta equals, roughly, the through current, the input to output current. Now what about a PNP transistor? So the input to output circuit will be the same, except I'm going to put the LED and resistor after the PNP instead of before it. So we'll go from positive power, the input of the PNP transistor, then from the output of the PNP transistor into a 1K resistor, from there into the LED into the negative power. Then I will connect from positive power into a 1K resistor and out that 1K resistor into the base. And I'm going to turn the current up, and what you should see is nothing. It goes to 5 volts and stops with 0 current because this is a PNP transistor. I have connected positive power to the top, the input, positive power to the base, which is not forward biasing that connection because it's in reverse. I'll switch it to negative. Now it turns on. I need to change the sensitivity back up. So you'll notice several things. First of all, it's on because I've connected it to negative power. No, I did not forget. I did it that way on purpose. So it's about the same brightness, but you'll also notice this current is higher than before because we've connected it to the total. Notice it's about that. This is the total going through. This is base plus input and output. And then this is backwards because the current, this is the base current, remember, minus 4.08 milliamps. This is going backwards from the emitter to the base and through into the negative power it's connected to. So let me rewire this to make more sense. So I'm going to connect from positive power over to the input of the PNP transistor. From the output of the PNP transistor, I'm going to connect to a resistor, the output of the resistor to the input of the LED. Then I'll connect the meter through to the negative. Now I'm going to turn it up without connecting the base, and you'll see the transistor does not turn on. Despite the fact that this is technically connected to 0, the base of the transistor is connected to 0, but it's not, remember, we're thinking logically. Physically, there's no current, which means the transistor is not working, and also, it's not actually connected to anything, it's floating with no current. So that's a trap you can get into if you're more of a programming type than an engineering type like me. We think of this as 0. We think of disconnected as 0. It's not. Disconnected is nothing. It's null. So I'm going to connect the positive of my meter to the base, the negative of my meter, and I should, of course, have turned that off because we're getting wiggle stuff. The negative through a resistor, and that resistor through to negative power, and now the LED comes on. We're showing 6 milliamps going through the power. We're showing 4 through the base and 2, and you'll notice it's about the same number going through the transistor. 2.22, 2.23, that's about what we were getting before. So now I will change the resistor. Instead of 1K, we do 10K. 0.42, 2.22. Let's go to the 150K. 2.15, turn this down. 28.3. Are you recognizing these numbers? How about the 1 mega ohm? Aha! 0.88, 4.2. So this is the same. 4.2 microamps. But now we're getting 0.88 milliamps through the LED instead of the 1.33 we were getting before. So up until we got to these low numbers, both the NPN and PNP were behaving the same way. Unsurprising because they're just reversed and made by the same company at about the same time, in the same size and package. But now when we get to much lower numbers, we're getting a different curve of beta. So when we use beta as a number, it's still roughly about the same, it'll work just fine. But if you look at the curve, and your spec sheet, a better spec sheet will probably have an actual curve for what beta really is. There you go. This one's slightly different when you get down to lower numbers. But that's the difference between NPN and PNP, the wiring. But it works the same way. You forward bias the base to emitter junction to turn it on. You don't forward bias the base to collector junction. That leaves it in active mode rather than saturation. And then the higher the current in the base, the higher the current through the thing, through your load, until you reach as much as the circuit will put through. So you reach effective saturation due to the amplification before you reach actual saturation mode. Because you're not going to reach saturation mode without changing the biasing of the base to collector junction. But you can keep turning the current up without doing that. You can always reduce resistance if you can't increase voltage. And that's it. So that is a transistor in amplification mode. A regular transistor, not a MOSFET or anything else, just a simple transistor. It's a current amplifier. When you hear amplifier, there's all kinds of fancy stuff all the way to op-amp, I think that stands for operational amplifier, which is a complex circuit used in many applications, in fact. But this is a literal amplifier of current, in effect, and is the building block for these other forms of amplifiers. This is the one that's really important that you're going to use in a lot of different places. We'll get to the more complex circuits in the future. Until then, be seeing you.